So good evening. What I'm showing you right now is a little screenshot of the handout that you should be reaching for. You can use your notes if you'd like from the regular PowerPoint edition, but this particular handout has space on the last page in which you will be solving for some specific problems. And these are the problems that I'm going to consider to be verification that you watched the Vodcast and completed those problems as instructed. So let's take a look at a slide here that shows the behavior of real gases. So when you look at this graph, the first thing I want you to notice is that if you have 1 mole of a gas and you rearrange the ideal equation to solve for that, N should be equal to PV over RT. If you have 1 mole of a gas, then this basically, under ideal conditions, is saying that the value of PV over RT should equal 1. Let's let that be our baseline. Let's pretend that this line right here, or let's assume, represents the behavior of a real gas of an ideal gas, assuming that you have 1 mole of it. So any values that register either above or below that line are what we call deviations from ideal behavior. So for a moment, if you look off towards the right, you can see that as the pressure increases, moving from left to right, here's the pressure, this value that should be 1 actually comes out to values greater than 1, and the greater the pressure, the greater the deviation from ideal. Also, if you take a look at the graph that shows temperature variations, this time's a little bit more subtle. We still have pressure here, and we still have the PV over RT equals the 1 baseline value, but now we're looking at the same gas at very different temperatures. And essentially what we're saying is, if you look at all 3 of these lines, when the temperatures get lower, then the behavior is going to be more nearly ideal. There'll be less deviations from ideal. So what we want to do is ask why that is. And the general reason stated in plain English is that those assumptions that we made, individual molecules have no volume and there are no attractive or repulsive forces, that wasn't a true assumption. And in fact, real gases at low pressure would occupy something like you see here. They can pretty much take up, this is low pressure, they can pretty much take up the whole space of that container. The volume of each of the individual molecules, because they're so far apart, is small compared to the total volume of the container. So basically they have free rein to roam over that entire volume of the container. But if you increase the pressure, as shown in the picture in the middle, now what you've done is you've made the free space available to them much less. And in fact, on a percentage or on a fractional basis, those gas molecules are taking up a much greater fraction of space. Now what happens when you do that? When you increase the pressure, so let me go back and tune that in a little bit, that means that this assumption that each one has essentially no volume gets less and less of a true statement the more and more you crowd them into a smaller space. The other thing that can happen is when they are crowded into a small space, pretend that this molecule here, or atom, is ready to collide with into the wall of the container with a certain force. But if it has some attractive forces that have increased now because you jam them closer to each other instead of being very widely spread apart, now they will have attractive forces to nearby molecules and perhaps might not strike the wall with as great a force. So basically what can happen is that the pressure that would be occurring there would be less than if it was in an ideal condition. So what we can do is we can factor in these gases really do actually have a volume, and secondly, they can have interactive forces with each other. We can take that into account by creating something called the van der Waals equation. And in this van der Waals equation, essentially you'll be given a table with values to consult that will correct for the factors that we just described. Now this is a slide from the old textbook, so there might be some formatting issues. Try not to get too stressed by it. But essentially what you're going to see is something familiar, the remnants of our PV and RT, and something new, a little letter B and a little letter A. When you factor in that gas molecules actually do have a volume, especially when you crowd them into a smaller space, that's what the little b factor here does. And you can have this A constant, which will correct for the fact that when crowded close to each other, the molecules can actually have intermolecular forces of attraction. So where we would be right now is looking at what your new version of the textbook describes as the best equation to use. Any of these will work as long as they're formatted right. And you can see that different gases have different A and B van der Waals constants. And the units that you see in there, again, if you're being good with your units, on this kind of problem it wouldn't be easy, they'll help cancel out everything except for the value that you are looking for. So once again, to repeat, A's are going to correct for the fact that there is intermolecular force of attraction, and the B values correct for the fact that there is a particular amount of volume in liters per mole of each of these individual real gases. Okay, so at this point in time, let's take a look at what I'm expecting you to do using the data on this table and the van der Waals equation. At the bottom of the last page of the handout that you're currently working on, there's a question that says, use the van der Waals equations and the values in the table to calculate the pressure of 1 mole of chlorine gas in a 22.4 liter volume at 0 degrees Celsius. And this will be outlined in sample exercise 10.16. So please go to a textbook and locate that. And we're going a little bit backwards. Go to the bottom of that page and complete that problem. I will not be doing that with you right now. In addition to that problem, please notice this screenshot of right above that, where you're being asked to calculate, using the ideal gas law equation, the pressure of 1 mole of carbon dioxide. This time the volume is 3 liters and the temperature is 0 degrees Celsius. When you walk through the door tomorrow, I will be looking for this entire sheet to be complete, to be able to get credit for having done the Vodcast tonight. Notice that on the ideal gas equation, you're going to be using your PV equals nRT, and there will be an answer I'll be looking for as you come through the door in atmospheres. And then I'd like you to take the van der Waals equation as shown on the previous slide and plug in the same values and calculate what that pressure would be if it was operating under the assumption that it's not an ideal gas. And essentially that's it. So tomorrow, make sure you have your multiple choice questions done that were assigned for homework. There's only 10. They're fairly straightforward. Shouldn't be too much of a problem. Copy one sample exercise at the bottom of the sheet and do the plug in and chug out the answers using Pivnert and using the van der Waals equation for the data that you see here. I believe that's it. Take care, and I will see you guys tomorrow.